That never for me gentle. Still rap for who's locked up and pour a shot for who's gone. Still sending that commissary.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So weak acids and bases are only partially ionized in their solutions, whereas strong acids and bases are completely ionized when dissolved in water. And so let me show you an example. Acetic acid, which we talked about before as being a weak acid, in the presence of water, dissociates into the H3O plus ion and the acetate ion. So if we write out the equilibrium constant for this equation, it would be H3O plus CH3COO minus as the products over the reactants, CH3COOH. So remember, since we consider dilute solutions, water is in large excess and considered a constant. And so the equilibrium constant is written without the presence of the liquid water. And this is actually given a different constant called Ka, which is the acidity constant. And this acidity constant is often called the ionization constant or dissociation constant. So a proton transfer equilibrium can also be written for a base in water. And so as an example, we have NH3 in water going to the ammonium ion, NH4+, and the hydroxide ion, OH-. So in this case, the equilibrium constant would be the products, NH4+, OH-. Again, for the reactants, we have water in large excess, thus a constant. The liquid is not considered, and we just have the ammonia. And this is now given the constant Kb, which is called the basicity constant. So this makes sense, right? Where Ka, the acidity constant, is talked about when we write out the equilibrium constant of a weak acid reaction, whereas the basicity constant is when you write out the equilibrium constant for a weak base dissociation. So as an example, the Kb for ammonia in water at 25 degrees is about 1.8 times 10 to the power of -5. So as you can see, the acidity and basicity constants are often reported as their negative logarithms. So the negative log of Ka is the pKa, and the negative log of the Kb is called pKb. So from looking at Ka, the acidity constant, and Kb, the basicity constant, I now wanted to introduce you guys to the conjugate seesaw. What this says is that the stronger the acid, the weaker its conjugate base. And then the stronger the base, the weaker its conjugate acid. So now we will derive a quantitative version of this seesaw relationship. So let's use the ammonium ion example again. So NH4+, which is aqueous, plus water, going to ammonia, NH3, plus H3O+. In this case, although we saw this in a reaction that was a base before, since we're starting out with a positively charged ammonium ion, this is the acid. So if this is the acid, the ammonia is going to be the conjugate base. And the Ka for this is going to be very simply NH3, H3O plus over the ammonium ion. Okay, but on the other side, if we started out with NH3 like we did before, and then water, and this goes to the ammonium ion plus OH minus, excuse me. All right, in this case, the ammonia is the base that we start out with, and then the ammonium ion is going to be the conjugate acid. And in this case, you have this hydroxide ion. In this case, you have the hydronium ion. And so in this case, we write out the basicity constant Kb as NH4 plus OH minus over NH3. So from here, I'm going to derive the Kw equation. Remember, Kw was the concentration of H3O plus and OH minus. And this is also going to be written as Ka times Kb. Why? Let's write it out. Ka is NH3, H3O plus over NH4 plus. And this multiplied by the Kb, which is NH4 plus OH minus over NH3. You can probably see where I'm getting at now, where you can cancel out the concentrations that occur on the numerator here and the denominator here, since we're doing a multiplication right here. So the ammonia, and the ammonium ion can both get canceled out, and lo and behold, you end up with H3O plus multiplied by OH minus, which is what we have right here. So from here, we can just simply write out the Ka multiplied by Kb equals Kw, which is 10 to the power of negative 14. So we were able to show you that this derivation is correct by actually making up these two acidity constant and basicity constants, multiplying them out so that you can cancel out the numerator and the denominator that occurs on both sides of the multiplication, and you end up with the hydronium ion concentration and the hydroxide ion concentration. And when you look at this relationship, you can see that as Ka increases, Kb would decrease. The same thing can be said where if you increase Kb, Ka would decrease. We can also take the log of both sides and get pKa plus pKb is pKw. So all of these relationships are going to be really important when you start solving different equations.
Bro, I don't never trust that. Just ride around my city with my top down, getting top. We'll never need handouts.